Okay. So, last few slides were on point to point transfer, right, point to point communication, not. Okay. Now, we will do some collective communication. So, that is what I want to do. Collective means here all the processors in the communicator will be involved. So, one simple example is broadcast, radio broadcast, right. So, everybody is listening, one person is talking, or summing up data from all the processors. Okay. So, they are collective communication, which are very important. I mean that. So, we will cover some of them, not all of them, ones which we need. So, broadcast. So, the function is bcast. This is the function, okay, bcast function. So, it will broadcast data to all the processes of the group, simple, nothing. So, I illustrate using this diagram. So, there are 4 processors which are numbered 0, 1, 2, 3 in that direction in the data. Okay. So, I will use 4 data. Okay. It could be string or number, 4 number, only 4 data. Okay. We could do more complex stuff, but right now I am simplifying it, 4 data. So, data in process 0 is A0. So, process 0 contains some number called A0. I want to broadcast it. So, the A0 should go to everywhere, single number. So, as a result of this transfer, A0 is there in all the 4 procs, right. So, that is what we will do. So, that is the output. So, syntax is pretty simple. First, you need to create the buffer. Even if you do not create buffer, send buff, okay, send buff, it is okay, it works, Python works. In C, that is why you need to have more lines, but in Python it works. So, if rank 0, then I am sending, I am create this buffer 1024, otherwise none, none is empty. So, com.bcast, and what you want to send, what you want to broadcast, and who is broadcasting, root equal to 0. So, root is broadcasting, but root need not be 0, root could be 1, 2, 3, anybody can be a broadcaster, it is allowed. But I am using a master, it is typically is good idea to be using master for all this work, but it is not mandatory. And where is it stored? In receive buff. By the way, send buff according to this syntax, and receive buff is variable for all the processors, okay, there with everybody. So, receive buff is there with every processor. So, I have 4 receive buffs, one each for each processor, and I print them along with the rank and the receive buff. Simple. I mean, these are just 4 lines. Well, of course, before that there are, you need to do all that, create the communicator, then rank and the number of procs. So, 3 lines are typically common. We need to get the rank and define the communicator. Okay. So, this is output, rank 0, the receive buff is this, rank 1, that. So, everybody has getting the same number, is broadcast, so same number. It is just a number, integer. So, this is the program which is running on all the processors. Okay. So, in process 0, what does it, when it runs this, what will it do? It will run this. Okay. So, by the way, process 0 is transmitting it, but also receiving it, because by definition broadcast comes to everybody. So, process 0 will receive buff, that is for process 0. So, this is the memory of process 0, 4 memory blocks. These are process 0, process 1, process 2, process 3. They are separate memories. So, process 0 and process 0 will print. So, process 0 is printing this line. Okay. Process 1 runs the code. So, it says process 1, well, I need to do nothing here, it will create send buff, but it is empty. Then receive buff. So, bot vcast, well, I am not sending. So, the guy is just saying, well, I am just going to receive. So, process 1 receives, what number does it receive? 1024, and stored in receive buff of process 1, 1024, and process 1 prints this. So, please keep in mind that this code is running on all the processors, and each of them has to receive, but only one of them is sending, broadcasting. Okay, and this is done in one line, this line, and is being executed by all the processors. Is that clear? And this is this is a parallel thinking. That is what you need to be used to it. And one important thing is multi-threading or GPU. We don't need to worry about the send receive. Which int?
Print.
No. Print is separate. Print is just usual print. Yeah, print, and receive buff is a variable, integer variable. So, print that. No, you are mistaken. Each guy has only one number. There is no loop, because in my laptop all the 4 processes are running simultaneously. So, my screen is controlled by all the 4 processors. So, imagine that 4 students are doing writing on the board. All of them are allowed to write, and they write their lines on the board. So, it is not done by one processor. These 4 lines of printing is done by 4 different processors. 4 different students are writing on this. Okay, you can just simulate by 4 people doing it. So, that is why I said these 4 processes are running simultaneously, and they access, of course, they have access to printer, all of them, single printer or single monitor. Yes, so you have to initialize here. Whatever you want to send, you put it here. I could have put 5000, but 5000 will print it, all of them will print 5000 then, not different numbers. So, here it is a sequence, but it is possible that rank 3 was printing first. Whoever gets access to the console or the monitor will print first. In HPC system, of course, you do not print like this, but yeah, there also we print, but not very often. But yes, you can print. So, this is a usual print, nothing complicated. MPI is doing only this is the function of MPI, nothing else. It is handling communication, and MP is also a Python function like sine, cos. Okay, it takes care of communication. Clear? Well, let us wait for GPU to come. So, threading we did not need all this, right? Threading was doing parallel, but only one function was doing parallel according to what we had designed. So, threading did not involve all these communications. So, that is why threading is multi-threading is easier to handle or think. And this you are thinking about 4 lines, but if you have a lot big program, then you see it requires bit of design thinking. Okay, scatter. So, scatter function scatters elements of an array to the processors according to the rank. Okay. So, illustration. So, process 0 has 4 numbers, it is an array, list actually, it is a list. Okay. So, 4 numbers, I want to scatter it. So, scatter you understand, no, the word is scatter. You send it like 4 numbers, so one each to each processor. Okay. So, 4 bullets you can fire to 4 processors, but 1 bullet each, and they are different bullets. Okay. So, this is A0 will come to process a 0, A1 here, A2 I can make a pentagon if you like, hexagon, A2 here, third, and this is double circle. Okay. So, this comes here. So, it is scattering the data. So, but the data size of the array size should be same as number of processors. Okay. Simple. Is useful sometimes. In fact, we will come to one example where it is useful in scatter. Okay. So, example is again now I thought some people are confused, but just the same code will run all the processors, and array to scatter rank 0 is handling it. So, rank 0 handles this array to scatter. It has 4 elements A, B, C, D. Okay. And other guys, this variable array, so array to scatter is none. So, these variables exist in all the processors. Okay. A receive buff com dot scatter, this one is here, and who is sending it or who is scattering it, not saying who is scattering it, root 0, root equal to 0, this one. Okay. And each guy is printing. So, what is the output of print? Rank 0 will print what? A. Rank 2 is C. Okay. And so, that is what is going to happen, all 4 of them. In fact, it turns out they are all in sequence, but they need not be in this sequence. A, B, C, D is being printed by the 4 processors respectively. Okay. Simple. So, this is for scattering. Now, we can gather. Gather is just opposite of scatter. Okay, this is gather. So, this process P 0 has A 0, P 1 has A 1, P 2 is A 2, P 3 is A 3, one number each. So, MPI, by the MPI is a complex task. I mean, so MPI will assemble it and put it on processor 0, processor of given rank. In this example, is putting in P 0. Okay. So, you will create a list of these 4 elements and put it in some variable location where of given rank. Okay. So, gathers all the data from all the processors and sends it to the root. Okay. Just the opposite of that, right. I mean, that is why I use the same picture. So, so I create data as rank squared. Okay. So, they are single number integers. So, numbers are 0, 1, 4, 9. So, gather. So, this data is, each guy is passing the data to this function gather, is collective. So, this gather is working with all of them and is being sent to root equal to 1. So, this is not a master node, it is a one of the workers, second processor, and then I say print rank equal to 1 will print. So, only one guy will print. I could ask other people to print, but that will be basically null. Okay. So, what is gathered? So, 0, 1, 4, 9, that is coming as an array. Okay. You can try out with yourself, you put rank equal to 0, you will see what happens. Okay. It will not be this, it will be null. Clear? All gather. So, all gather is just like gather, but everybody gets it. Everybody gathers their collected thing. Okay. In our HPC, we do not need all this stuff. Well, I didn't need, I never use gather really. But lot of this computer science stuff requires that. Okay. So, we have 4 data A 0, B 0, C 0, D 0 and they are gathered. So, they put together one list, right. So, this is going to P 0, but it is going to all the processors. So, P 1, P 2, P 3, all of them are getting it. Okay. So, all gathered. So, sends the collected array to all the procs. Okay. And I didn't write a program for this, but you can write yourself and you can print it. Okay. Let's see that. Now, this is important function all to all. So, each processor redistributes this data equally to all other procs. Okay. Now, so this is a complex function. Now, processor 0 has data A0 to A0, A1, A2, A3. Processor 1 has B's, C's and D's. I want to equally distribute. So, P0 has A0, A1, A2, A3. So, what will it do? It wants to give this to P1, this one to P2, this to P3. Okay. Same thing for processor 1. It will keep this one because it is the second and so 0, 1, 2, 3. So, it is going to distribute. So, you can check where should A 3 be in P 3, So, A 3 is here, this processor, third processor P 3, A 2 is coming here. So, this row has become a column, this row will become a second column, this row will become third column, and this row will become fourth column. So, this transpose really, okay. For a number or for a string it will be transpose. Great. Sometimes this is not a number, but it is an array. So, imagine we have something like 64 by 64 array, but are only 4 processors. Okay. So, it is 2D array, but 64 by 64. So, each guy will get 8 by 8 chunks, correct. 64 by 4, no, 16 by 16. So, 16 by 16 will be the blocks of each of these guys, and we can do transpose with that as well, but you have to be careful, is simple transpose does not work here. So, this column has to become a row. So, when I do this all to all, it will just put the block, but it does not do the local transpose. Okay. So, for bigger data you need some more operations, and this is operation in fast Fourier transform. Okay, that is why we know this very well. FFT requires all to all. Okay. And so, right now we just work with 4 objects. So, this is this syntax is slightly non trivial. So, send data is rank plus 1 star A arrange. So, I wanted to create numbers, so which is easy to visualize. So, rank plus 1 will be instead of 0 to 3 is going to be 1 to 4, and A range will give us number A range n procs. What is it going to give you? Number of procs is 4, so it is going to give you 0, 1, 2, 3 and is integer. Okay. So, my array is, you just focus on the left one, send data, all of them will create send data, but rank 0 will create what? This is 1. So, 1 multiplied by 0, 1, 2, 3. So, you get that. Rank 1, which is second processor, which is going to be 1 plus 1 is 2, 2 multiplied by this, which is 0, 2, 4, 6. Third processor is 3, 6, 9, and fourth processor is 0, 4, 8, 12. Okay. Now, receive data I will keep it empty, and then I do all to all. So, all to all will send data. So, by the way, this array, this big array is not sitting in one processor, it is sitting in 4 processors, piece by piece. So, you need to divide your data among all of them. So, there are 4 rows and they are sitting there. Now, receive data. So, this is going to be received. So, process 0 will send this, process 1 will send, well, basically will distribute. So, after distribution I expect this array to be stored like that. So, process 0 will be 0, 0, 0, 0. This guys will become process 0. Transpose, no? That is what we said. This guy will become process 1, which is process 1. So, it is transposed literally all to all for a single data, and this is what we will get. Okay. So, I printed it here. The print is in the next slide. Well, I do not have it here, but basically you can print and you will find the first will give 0, 0, 0, process 1 will give you 1, 2, 3, 4, process 2 will give you 2, 4, 6, 8, and the last one gives 3, 6, 9, 12. And this is an important function, COM barrier. So, all the processes in the communicator must finish the task before crossing the barrier. Okay. And I told you, I mean, basically if you finish one task and you go to the next, you have to make sure that all the processes are done, so that all the data is updated, and then we go to the next. So, your function like your finite difference code, you need to finish one thing, then go to the next. So, we need to do that. Even printing, well, this one is one task, but imagine we have several tasks and you print them. So, it is possible that task is not complete and is asynchronous or non blocking. So, it will print number which is not updated. Okay. So, block will make sure that data is all perfect and we synchronize all the process. So, everybody is ready after block, after barrier. Okay. Sometimes it may work, but do not go by that. Always be careful with large codes, do not deviate from the simple syntax. The reason is some guy may handle it, but it will not be a general, it will not be a reliable code. Some machine it may give some different result, some other machine give some different result. So, large codes we have to be careful, and this thing is called portable. The code must be portable. You can't say it runs on IIT Kanpur machine, but not in IIT Bombay machine. Okay, so that should not happen. Okay, so let us finish this reduction operation. Okay, ready? So, reduce is a very important function. For example, I have local sums and I want to add them. So there could be in fact million processors or 100,000 processors. We have local sums. I do not want to get one by one. That is too much work for the programmer and also for the system. One by one things are coming. So you can say local sum. You can reduce them. You can do a sum on all the data. So this is called reduction operation. Okay, we will do one operation, but it will get the result by operating this operator, but it is not going to do one by one. So, it is going to do something like a tree. It will divide the data into number of procs, half, then half of is further divided. So, you get, so this is going to be done by MPI, not you. So, it does in such a way that you do not need to communicate a lot of these local sums. Each communication is expensive. So, the syntax is reduce function. So, whatever data I want to operate on has to be sent to MPI, okay, not sending to anybody per se. The final result is with somebody, with the root final result, and that is received data. So, this is like partial sum, local sum, this is sum, okay, and operation is MPI dot sum, and who is collecting it? Typically master. So, I can say 0 or anybody could collect, not a problem. Okay. So, process wise operation on send data arrays. There are other operations like max, min, product. Okay. I can do a product as well. A product, be careful, a product can be a very big number and it can overflow. Some also can overflow, but yeah, that is what you need. Well, Python never overflows, you know that, right? Python never overflows. It just takes lot of adds. It creates more and more data, bytes, but C will overflow. And we can also do logical AND or logical OR. So, with the data. Okay, so this is the code, same example, rank plus 1 E range, and receive is empty. So, I am sending this, each guy will send to MPI, receive it, and sorry, got cut, root is getting it. Okay. So, we have the data created. So, this same as before. So, 0, 1, 2, 3 in P0, 0, 2, 4, 6 in P1 and so on. Now, sum, so local sum is a single number, but you can also sum in array, sum arrays, not array, in array. So, I am going to sum all the 4 arrays, but element by element. So, P0 will sum the first element of all the arrays. So, 0, 0, 0 is 0. Next one is second entry in the arrays 1, 2, 3, 4, which is 10, 20, 30. Okay. So, we can also add arrays, I mean you can do this MPI sum on arrays. collective operation, and other operations will be pretty similar. So, I did not I am not showing you here. So, this is the reduction operation.